In this video, we're going to go through the entire first semester study guide for Chem 1. All right, so let's start with the first question. It says, describe the structure of an atom. Where is the most mass? Where is the most volume? So with an atom, you have the nucleus and you have the electron cloud or the orbitals. So let me just draw a little atom here. Okay, now let's do this. So in the nucleus, that is the middle of the atom. That's where the protons and neutrons exist. And that's where the most mass is. So the protons and the neutrons make up the majority of the mass in an atom. And the electrons are in the electron cloud, and that's where the most volume is. So if you look at my diagram, that little X in the middle, if that represents the nucleus, that's a pretty confined space, but then as you start to get further out where those rings are, there's a lot more space, there's a lot more volume there. Everything's really spread out. All right, next question. It says, how is the periodic table arranged? So the periodic table is arranged by the number of protons. So number 1 is hydrogen, it has 1 proton. Number 2 is helium, it has 2 protons, and so forth. Number 3, determine the number of protons and neutrons in the nucleus of carbon-14. So carbon is number 6 on the periodic table. So that means it's going to have 6 protons. 6 protons. Okay. That is the mass number. The mass number is equal to the protons plus the neutrons. So if the mass is 14, and that's equal to protons, which we know are 6, plus the number of neutrons, I would subtract to get the number of neutrons. So 14 minus 6, we're going to have 8 neutrons and 6 protons. Okay, determine the number of protons and neutrons in the nucleus of lead-208. So 208 is the mass number. That's equal to the number of protons. Lead is 82 plus the number of neutrons. So I would have to subtract here. So 208 minus 82 is 126. So there are 82 protons, 126 neutrons. Okay, element A has 3 isotopes. The first has an abundance of 20.04% and a mass of 225.11. The second has an abundance of 45.23 and a mass of 226.10. The third has an abundance of 34.73 and a mass of 228.11. So, to calculate average atomic mass, we are going to multiply each mass by its abundance. I want to turn each percent into a decimal. So I can take the percents and divide them by 100, or move the decimal place 2 places to the left. So I'm going to do that for each one. So I have 0.2004 times its mass, which is 225.11. I'm going to add that to the next one. So I'm going to move my decimal place 2 times to the left, 0.4523 times 226.10. And then the third, 0.3473 times 228.11. Okay, so I'm going to do the math on my calculator here. 0.2004 times 225.11 plus 0.4523 times 226.10 plus 0.0 0.03473 times 228.11. And I get an answer of 226.60 as my answer. Okay, so that answer looks reasonable because it is between the lowest number and the highest number. So my lowest number is 225, my highest number is 228. So when I take an average, my number should be between those two numbers. If I got an answer of 7,000, that doesn't make any sense because it is way outside the scope of our average. Okay, next question. Rubidium has two common isotopes, rubidium 85 and 87. The atomic mass of rubidium is 85.5. Predict the approximate abundance of 85 and 87. So I'm going to do this on a number line. So here is 85. Here is 87. And in the middle would be 86. And our average is 85.5. So right here. All right. So if it was 50-50, if it was 50% 85 and 50% 87, my average would be 86. It would be right in the middle. But it's not. It's closer to 85. So what about if I did 75% 85 and 25% 87? 85 has a little bit more abundance, so my average is going to be closer, and that's going to move my average kind of between 85 and 86. Okay, so I would do it on a number line and look at what 50-50 would be like and then kind of work it from there. All right, Unit 2, what is the purpose of a flame test? What can the colors produced help us identify? So the flame test is a qualitative test, meaning that it's on observations, and we are putting a sample into the flame, and we are exciting those atoms. So the electrons start in the ground state, and just make a note here. Yep, so they start in the ground state, and we excite the electrons. So the electron moves to a higher energy level. So it moves to a higher energy level. And then it doesn't stay there. It's got to come back down. And when it comes back down, it emits a photon. And a photon is a light particle that our eye picks up. And depending on the wavelength, they represent different colors. So the colors of the flame test help us identify the different metals. So each atom has a different differences in energy levels, and they're going to produce different colors of light. And again, we use the flame test to differentiate between different elements. Okay, write the electron configuration of a nitrogen atom and a calcium atom. Okay, nitrogen atom and a calcium atom. Okay. So nitrogen is number 7 on the periodic table. Okay, so nitrogen is number 7 on the periodic table. So we always start up here at hydrogen. Okay, so hydrogen is our 1s. So nitrogen is number 7, so it has 7 electrons. And we always go in order. So it's always 1s, then 2s. Okay, and then if you're following along on the periodic table, after 1s, 2s, then we go across the periodic table. This is 2, and this is the p block. Okay, s will hold 2. P will hold up to 6. So nitrogen has 7. So 1s, 2. I can put 2 there. Then we go to the 2s. That'll hold 2. And I have 3 electrons left. So it is going to be 2p3. I only need 3 there. 6 is too big. Okay, calcium on the periodic table is right here. It's number 20. It's in the 4th row. So after 3s, it's 3p and then 4s. So 3s, 3p, 4s. And then remember, the D block, which we didn't get up to in this example, will hold 10. And the thing to remember about the D block is it is always one behind whatever row you're on. So calcium is number 20, so it has 20 electrons. So 1s2, 2s2, 2p6. That's 10 electrons. So 3s2 is 12. 3p6 is 8. And then 4s2 is 20. Okay, elements that have the most similar chemical properties are usually found in the same group. And the group is the same column on the periodic table. So this is our first group right here. Okay, which elements on the periodic table are the least reactive and why? So the least reactive are the noble gases, which are this last column all the way on the right side. They're the least reactive because they have a full shell of valence electrons. So when I draw my atom, first one holds 2, the second one holds 8, so it has a full outer shell. So every single electron that needs to be there is there. So it is a full valence shell. Now on the periodic table, whatever group number you're in is the number of valence electrons. So using ptable.com, these are numbered 1 through 18. So the number of valence electrons doesn't exactly match up, but if you count them from left to right and skip the D block, it goes 1, 2, 3, 4, 5, 6, 7, 8. That tells you the number of valence electrons. And the first one was oxygen. So oxygen is 1, 2, 3, 4, 5, 6 valence electrons. Calcium is in right here, and it is in the second group, so it's going to have 2 valence electrons. Chlorine is in group 7. It's going to have 7 valence electrons. And then rubidium, Rb, is right here. It's in the first row. It is going to have 1 valence electron. Sorry, not row, group. All right, which 2 types of elements will join to form an ionic bond? That is going to be a cation, which is positive, and an anion, which is negative. Okay, so we know that calcium has 2 valence electrons. So if I were to draw a Lewis dot structure, it is going to have 2 dots, just like that. Nitrogen. I go and look at my periodic table. 1, 2, 3, 4, 5. Gets 5 dots. And we always want to go around and give each side 1 before we start to double them up. You should never have 2 lumped on one side if you don't have enough for everybody. Okay, phosphorus. 1, 2, 3, 4, 5. Phosphorus is also 5. Okay, next question says, draw a Lewis dot structure for lithium oxide. Be sure to include the correct number of each type of ion and the charge of the compound. Okay, so lithium, Li, is in group 1. So it gets 1 dot. Oxygen has 6. 1, 2, 3, 4, 5, 6. So 1 from lithium will go to the oxygen, so oxygen is happy. But oxygen still needs 1 more. So I'm going to add in 1 more lithium. And lithium's going to give it up. So all of the cations, so anything that has less than 4 valence electrons or 4 dots is going to lose those electrons. Anything that has 5 or more is going to gain those electrons. So if I were to draw this out, lithium gave up its electrons and it ends up with a +1 charge. And there are 2 of those. oxygen gained, so it now has 8 valence electrons, and it is gaining 2 electrons, so its charge is going to be -2. All right, write the formula for the following ionic compounds. Okay, when you are working with ionic compounds, if it gives you Roman numerals, that tells you the charge. So copper here is +2. Oxygen is -2. Sorry, it should be 3. So I want to make sure my charges cancel out. If I put 3 and 2 together, they don't cancel each other out. So I'm going to need 2 coppers and 3 oxygens. 2 coppers times +3 is +6. 3 oxygens times -2 is -6. They cancel each other out. Okay, lead, 2. So lead is +2. Sulfate comes from our table of polyatomic ions. And if I look up sulfate on my table of polyatomic ions, that is SO4. And it is -2. So I'm just going to put those two things together. So PbSO4. All right, magnesium is in group 2. So its charge will be +2. Hydroxide, OH, is -1. So Mg, I'm going to need 2 of these to balance out. So it'll be OH and then 2. Now notice I put parentheses around the OH. By doing that, that's saying I have 2 of these. If I just wrote it like this, that's only 2 H's. So the parentheses represents having 2 of my OHs. All right, lithium, Li is +1. Oxygen, -2. So this will be Li. I need 2 lithiums to balance with the oxygen. All right, now let's do the opposite. Let's name the following ionic compounds. So cation goes first, so calcium. Bromine becomes bromide. We change the ending to IDE. All right, K is potassium. PO4 is, I'd have to look that up on my table of polyatomics, that is phosphate. All right, next we have magnesium. SO4 is sulfate. Okay, now this one's a little harder. So NO3 is -1. And there are 2 of them. So my total negative will be -2. All ionic compounds are neutral. So that means my Fe has to be +2. So this will be iron. Fe is iron. Iron 2. NO3 is nitrate. Okay, so these are all transition metals. So on our periodic table, transition metals are anything in the D block. We also include tin, which is Sn, and lead, Pb, in the same category because they have variable charges. So OH, for example, is -1, and there are 2 of them. So manganese has to be +2 to cancel that out. Okay, oxygen is -2, and there are 3 of them. So that equals -6. Chromium, there are 2 of them. So what times 2 gives you +6? Well, it would be plus 3, because plus 3 and plus 3 is plus 6. Okay, bromine is minus 1. There are 2 of them. So lead has to be plus 2 to cancel that out. Okay, predict the products of the following reactions. So we have magnesium, which is plus 2. We have lead, and I feel like we just did this one. I'm thinking of something else. Okay, so lead, Pb, is plus 2. And then NO3, minus 1. So this is going to be a single replacement reaction. I can't have 2 positives together, so magnesium will go with nitrate. So it'll be MgNO3, and then it'll have lead solid on the other side. Okay, when we balance, we split it into 2 sides. So let me zoom in actually to make this a little easier to see. And let's write out what we have. So on the left side, we have 1 of those, 2 of those. And on the right side, we have 1, 1, 1. So if I put a 2 here, that makes this a 2. That makes that a 2. Now my magnesiums don't match, so let's put a 2 here, and that becomes 2. We are balanced. Let's make our pen not so thick here for the next one. All right, same thing. Let's figure out charges. So we have magnesium, Mg. We have Cl, magnesium's plus 2, chlorine minus 1. We have lithium, Li, which is plus 1. And we have CO3, carbonate. You'd have to look that one up on your table of polyatomics. That is minus 2. So this will go with that, that'll go with that, and let's write it out. So it'll be MgCO3 plus LiCl. Let's balance. So magnesium, chlorine, lithium, carbonate. All right, so 1, 2, 2, 1, 1, 1, 1, 1. So this one's easy to balance. Let's just stick a 2 right here. That makes that a 2. That makes that a 2. Balanced. Okay, so this one's relatively easy because we have, oh, and that is a double replacement. We are replacing 2 things here. C, we have chlorine, which is minus 1. We have sodium, Na, which is plus 1. So this will just be NaCl, cation first. So split it in half, NaCl. So if I put a 2 here, that becomes a 2, that becomes a 2, that becomes a 2, and we're done. Okay, moving on to the next one. That last one, C, was a synthesis reaction. Just putting 2 things together. Okay, so the last one, we have NaCl, LiSO4. Na plus 1, minus 1. Lithium is plus 1. SO4 is minus 2. This goes with that. That goes with that. So we are going to have NaSO4 and Na2 because I need these to balance out. And then LiCl. Let's balance. Okay, 1, 1, 2, 1, 2, 1, 1, 1. So sodiums aren't balanced, so let's put a 2 here. This becomes 2. This becomes 2. We need a 2 here. That becomes 2. That becomes 2. And we're balanced. Okay, so ionic bonds are really strong because you have a cation and an anion. And I like to make the analogy of an ionic bond is kind of like true love in a Disney movie. Nothing is going to break that bond. It is very, very, very strong. Okay. If M represents a metal and NM represents a nonmetal, predict the charge of each in the formula M3N2. All right. So here you have 3 and 2. So M can't be plus 1 because if it was plus 1 and there were 3 of them, the total charge would be plus 3. If the same was true for Na, it would be plus 2. So this is actually a common thing that comes up where you're going to have to multiply them by different numbers. So if M is plus 2 and Na, that should be Nm, non-metal, is minus 3, plus 2 times 3 is going to be plus 6. Negative 3 times 2 is going to be negative 6. And they're going to cancel each other out. Okay, Unit 4 says classify the following bonds as ionic, polar covalent, or non-polar covalent. So for these, you would have to look up these values on the periodic table. So you will get a table of electronegativity values. So if I look these up, you always want to subtract the smaller number from the bigger number. So aluminum, for example, is 1.61 and oxygen is 3.44. So I actually did that backwards. So 3.44 minus minus aluminum, which is 1.61. So if I subtract those two numbers, so 3.44 minus 1.61, I end up with 1.83. And there's a scale at the bottom of the periodic table, and in that range, that is going to be ionic. C and F. So F is 3.98. C is 2.55. And if I subtract 3.98 minus 2.55, I get 1.43, which is polar covalent. And the last one, C and H. So C is 2.55. Hydrogen is 2.10. And if I subtract these, I get 0.45, which is nonpolar. All right, so it says complete the following table. Let's do this one at a time. So when you're drawing Lewis structures, you start by figuring out the number of valence electrons. So carbon has 4, oxygen has 6. There are 2 oxygens, so the total will be 12 here. 4 and 12 is 16. Carbon goes in the middle. Oxygen goes on either side. Carbon always goes in the middle. And let's bond. So 2, 4, bonding gives me 12. So let's put the 12 on the oxygens. Each oxygen needs 6. So they have 8. Great. So everybody here wants 8. All the oxygens have 8. Carbon has 2, 4. So carbon needs 4 more electrons. So if I take 2 from this side and double bond, that'll work. And if I take 2 from this side and double bond, that'll work. Now if you look at the structure, you've got carbon in the middle, oxygens on either side. Everything attached to the central atom is the same. There are no lone pair of electrons. This is going to be nonpolar. Okay, to figure out Vesper shape, there is a table that you're going to use in your resource packet. And for Vesper shape, there are 2 atoms attached, no lone pair on the central atom. So you just reference that page in your resource packet. This is going to be linear. All right, Cl2. So chlorine has 7 valence electrons. There are 2 chlorines, that's 14. Chlorine, chlorine. Bond them. I have 12 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I used up all 12. Everything's good. Now there are only 2 atoms. So there isn't a central atom. So when you have 2 atoms, it's like a tug of war, where you have 2 things pulling against each other. And in this case, they're both chlorine, so they're pulling with the same amount of force in opposite directions. So that will make this nonpolar. Okay, now when you only have 2 atoms, the only shape that is possible is linear. Okay, let's look at the next one. So we have carbon. Carbon is 4. We have bromine. Bromine is 7, but there are 4 of them. That'll be 28. 28 and 4 is 32. So carbon goes in the middle, of course. Bromine, 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 bromine. Connect everything. 2, 4, 6, 8. That leaves us, let's see, 24. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so all the way around, all the bromines have 8. Carbon has 8. Perfect. This is also going to be nonpolar. Everything attached to the central atom is the same. And if I go to my resource packet and look on the page, we have 4 atoms attached. No lone pair of electrons. This is going to be a tetrahedral. Okay, NH3. So we have nitrogen and hydrogen. Nitrogen is 5, hydrogen is 1, and there are 3 of them. 5 plus 3 is 8. Nitrogen goes in the middle. Hydrogen, hydrogen, hydrogen. 2, 4, 6. That leaves us 2 left. Hydrogen, remember, only wants 2 electrons. Nitrogen wants 8, so it has 2, 4, 6. It needs 2 more. So because of these last 2 that we just put out on the central atom, this is going to be polar. And 3 things attached. 1 lone pair. This is going to be a trigonal planar. Okay. For these, let's take a look. So Cl2 looks like this. N2 looks like this. O2 looks like this. Oops. Okay. I want to look right here. So we have a single bond, we have a triple bond, and we have a double bond. So think about rubber bands. If you have 1 rubber band, you can stretch it out with your fingers pretty far. If you have that same rubber band and you wrap it around, so it's basically like 3 rubber bands, you're tripling it up, it's not going to stretch out very far. So Cl2, my single bond, is going to be the longest, N2 is going to be the shortest. And then O2 would be in the middle because it is a double bond. Bond energy. So N2, the triple bond, is the strongest. It takes the most energy to break. Cl2 is the weakest. A single bond or a single rubber band is really easy to break. Okay, ionic and covalent compounds. Let's compare and contrast the properties. So ionic and covalent. So ionic compounds are a cation and an anion. Electrons are transferred. Okay, they have high melting and boiling points. Conductive when dissolved in water. Covalent compounds are nonmetals. So the right of the staircase. Electrons are shared. These have low melting boiling points. And these are not conductive. All right, let's name these. So for covalent compounds, we have our prefixes. We never use the prefix mono on the first atom. So in this first one, we have one carbon and one oxygen. So this will just be carbon monoxide. But look here. You never want to have these two O's next to each other, so we are going to drop one of these. So it will be carbon monoxide instead of carbon monoxide. Okay, N2O4. So 2 is the prefix for di, so it'll be di-nitrogen. Tetra is the prefix for 4, and then oxide. Okay, now again, O and the A next to each other, so we're going to drop the A, and it'll be tetroxide. Okay, disilicon. So this will be Si. Di is the prefix for 2. Hexa is the prefix for 6. So this will be Br6. Tetra phosphorus. So tetra is the prefix for 4. Penta is the prefix for 5. Okay, hydrogen bonding occurs between one molecule and HF, HO, HN. You have to have one of those bond types for hydrogen bonding to be present. All right, determine all intermolecular forces that would be present between two molecules. Okay, so for these, you need to draw these out. Since we already kind of went through drawing the Lewis structures, I'm just going to quickly draw these because I know what they look like. It's one of the perks of being a chemistry teacher. All right, so let me just fill these in here. Ooh, this one is a doozy. Should look like this. Carbon goes in the middle. Okay, I think that's right. Okay, so let's list the forces. So the first one here, everything attached to the central atom is the same, no lone pairs. This is nonpolar. Nonpolar, the only intermolecular forces you have are LDF. The next one, polar, because of the electrons here. Because it's polar, it gets LDF because everybody has LDF. It is going to get dipole-dipole because it is polar. And we also have HO, so it is going to have hydrogen bonding. Okay, the next one here. This one is polar because we have this, and this is different than the hydrogens attached. So this is going to be polar. It gets LDF because everybody has LDF. It gets dipole-dipole because it's polar. It is going to get hydrogen because of that little part that I circled or squared. Okay. The last one. This one is polar. Two things, not the same. It gets LDF because everybody has LDF. It gets dipole-dipole because it's polar. It does not get hydrogen bonding. Just because it has hydrogen doesn't make it hydrogen bonding. All right. LDF is the weakest intermolecular force. Then dipole-dipole. And then hydrogen bonding is the strongest. Okay, of course, they give us completely different elements here. So let's see. Let me just draw these out really quick. So we have HBr. That looks like this. Na2S is ionic. You have a metal and a non-metal. That is going to be the highest boiling point, most likely. Ionics are... Ooh, what happened here? Ionics usually have higher melting and boiling points than everything else. Okay, NH3 looks like that. And then Cl2 looks like this. Okay, so let's go through. And let's talk IMFs first, and then we'll talk boiling points. So the first one here, this is going to be LDF. Actually, this will be LDF too. And this will be LDF, because they're all LDF. This one is polar, so it is also going to get dipole-dipole. It's polar because you have two different things attached. This one will be dipole-dipole. Because it is polar. This one here is non-polar, so I stopped there. NH3 will also get hydrogen bonding. Because it has HN. So the lowest will be our LDF. Then dipole-dipole. Then hydrogen bonding. And then ionic. So even though I said hydrogen bonding is the strongest intermolecular force, that's for non-polar. That is for covalent. Ionic compounds still have the strongest melting and boiling points out of all of the compounds that we've talked about. Ah, look at that. We're done. That was so much fun.